Very good morning. In this session, we will discuss about convolutional neural network. The main objective of this session is to develop the artificial neural network based pattern recognition. At the end of the session, you can able to utilize deep learning models such as convolutional neural networks and recurrent neural networks for image and sequence classification. These are the reference books we will follow in this session. These are the topics for Unit 4. So let's start. Artificial intelligence has been witnessing monumental growth in bridging the gap between the capabilities of humans and machines. Researchers and work on numerous aspects of field to make amazing things happen. One of many such areas is the domain of computer vision. The advancement in computer vision with deep learning have been constructed and perfected with time, primarily over one particular algorithm, which we call it as convolutional neural network. A convolutional neural network is a deep learning algorithm that can take in an input, assign importance, that is, learnable weights and biases, to various aspects or objects in the image and be able to differentiate one from the other. The pre-processing required in a convolutional neural network is much lower as compared to other classification algorithms. While in primitive methods, filters are hand engineered without enough training. Convolutional neural networks have the ability to learn these filters or characteristics. The architecture of CNN is analogous to the of the connectivity pattern of neurons in the human brain and was inspired by the organization of the visual cortex. Individual neurons respond to stimuli only in a restricted region of the visual field, known as the receptive field. A collection of such fields overlap to cover the entire visual area. Next. So here an image we will say is nothing but a matrix of pixel values. So why not just flatten the image as given in the image? So in the given image, a 3 cross 3 image matrix is flattened into a 9 cross 1 vector and feed it to a multi-level perceptron for classification purpose. In that case, extremely basic binary image, the method might show an average precision score while performing prediction of classes but would have little or no accuracy when it comes to complex images having pixel dependency throughout. A convolutional neural network is able to successfully capture the spatial and temporal dependencies in an image through the application of relevant filters. The architecture performs a better fitting to the image dataset due to the reduction in the number of parameters involved and the reusability of weights. In other words, the network can be trained to understand the sophistication of the input better. So in this given figure, we have an RGB image that has been separated by its three color planes, red, green and blue. There are number of such color spaces in which image exists. It can be grayscale, HSV, CMYK, etc. Now you can imagine how computationally intensive things would get once the images reach dimensions, say 8K, that is 7680 cross 4320 pixels. The role of convolutional network is to reduce the image into a form that is easier to process without losing features that are critical for getting a good prediction. This is important when we are to design an architecture that is not only good at learning features but also scalable to massive data set. So here we are seeing a convoluting a 5 cross 5 cross 1 image with a 3 cross 3 cross 3 kernel to get a 3 cross 3 cross 1 convolute feature. Here the image dimension is 5 cross 5, that is the height and width, with number of channels, that is 1. In the amount in the given demonstration, the green section resembles our 5 cross 5 cross 1 input image. The element involved in the convolutional operation in the first part of a convolutional layer is called the kernel filter K, which is represented in the yellow color. So we are using a kernel K as 3 cross 3 cross 1 matrix as given here as 1010101001. The kernel shift 9 times because of stride length 1 every time pertaining an element-wise multiplication operation between K and the portion P of the image over which the kernel is hovering. The filter moves towards the right with a certain stride value till it passes the complete width. Move on, it hops down to the beginning of the left with the same stride value and repeat the process until the entire image is traversed. In the case of images with multiple channels, the kernel has the same depth as that of the input image. Matrix multiplication is performed Kn and In stack. That is K, K1, I1, K2, I2, K3, I3, and all the results are summed with the bias to give us a squashed one depth channel of convolute feature output. The objective of the convolution operation is to extract the high level features such as edges from the input image. Convolutional networks need not be limited to one use. Conventionally, the first convolutional layer is responsible for capturing the low level features such as edges, color, gradient orientation, etc. With the added layers, the architecture adapts to the high level features as well, giving us a network that has a wholesome understanding of images in the dataset, similar to how we will do. There are two types of results to the operation. One in which the convolved feature is reduced in dimensionality as compared to the input, and the other in which the dimensionality is either increased or remains the same. This is done by valid padding in the case of former and same padding in case of the latter. Same padding 5 cross 5 cross 1 is padded with zeros to create a 6 cross 6 cross 1 image. When we augment the 5 cross 5 cross 1 image to 6 cross 1 and then apply the kernel over it, we will find the convolved matrix turns out to be the dimension of 5 cross 5 cross 1. Therefore, we call it as same padding. On the other hand, if we perform the same operation without padding, then we are presented with a matrix that has a dimension of the kernel itself 3 cross 3 cross 1, that is valid padding. Next is the pooling layer. Similar to the convolutional layer, the pooling layer is responsible for reducing the spatial size of the convolved feature. This is to decrease the computational power required to process the data through dimensionality reduction. Furthermore, it is useful for extracting dominant features which are rotational and positional invariant, thus maintaining the process of effectively training the model. There are two types of pooling: max pooling and the average pooling. Max pooling returns the maximum value from the portion of the image covered by the kernel. On the other hand, average pooling returns the average of all the values from the portion of the image covered by the kernel. Max pooling also performs a noise suppression. It discards the noisy activities altogether and also performs denoising along with dimensionality reduction. On the other hand, average pooling simply performs dimensionality reduction as a noise suppressing mechanism. The convolutional layer and the pooling layer together form the ith layer of a convolutional neural network. Depending on the complexity of the image, the number of such layers may be increased for capturing low level details even further, but the cost of more computational power. After going through the above process, we have successfully enabled the model to understand the features. Moving on, we are going to flatten the final output and feed it to a regular neural network and for classification purpose. Adding a fully connected layer is a cheap way of learning nonlinear combination of the high level features as represented by the output of the convolutional layer. The fully connected layer is learning a possibly a nonlinear function of the space. Now we have the converted our input image into a suitable form for our multi-level perceptron. We shall flatten the image into a single column vector. The flattened output is fed to a feed-forward network and back propagation is applied to every iteration of training. Over a series of epochs, the model is able to distinguish between dominating and certain low-level features in images and classifying them using the softmax classification technique. These are the some of the applications of convolutional neural network: facial recognition, medical imaging, video analytics, natural language processing, object detection, image classification, etc. In summary, convolutional neural network is a type of deep learning neural network that is well suited for image and video analysis. CNN uses a series of convolutional and pooling layers to extract features from images and videos and then use these features to classify or detect objects or scenes. Thank you.